Am I audible?
Yes, sir.
So, did you all try out these assignment problems? Should we start with them first?
No, sir, I have not done. Kindly,
Okay,
sir, uh,
fine, I'll discuss them.
explain this.
Yeah. So for this problem, it's the requirement of the designer that uh, he needs an advice on discharging a 1 microfarad capacitor in his PCB from 3 volt to 1 volt. Okay, 3 volt to 1 volt. He also proposes two different methods for the same. Uh, The first of the method is exponential discharge from 3 volt to 1 volt in 50 microseconds. And the second one is a linear discharge from 3 volt to 1 volt in 1 milliseconds. Right? Uh, yeah, for exponential discharge, let's say you are given a MOSFET with this mobility, this Cox per unit area, and this aspect ratio and this threshold voltage. So you need to determine what is the value of the gate voltage that is to be applied. Okay, now it proceeds as follows. For your MOSFET, it has to behave the resistor for exponential discharge. Okay, so it's an RC, right? Capacitor is in series with this MOSFET, which will behave as a resistor. So now, for that, you need to bias your MOSFET in deep triode region. Okay, right? Biased in deep triode region. Okay, and your resistor behavior is independent of the VDS, right? So right R is equal to 1 over mu n Cx W by L, where VGS minus VT. Now, these quantities are given. This is also given. We are left with this, right? So we'll write, uh, if we simplify it, this will be 200 volt divided by your VG minus 1. Fine. This is the value of the resistance. Okay. Now, uh, coming to the voltage across the capacitor, right? If I denote that by V of t, since this is an exponential discharge, this would be your V of 0, the voltage across the capacitor at t equal to 0 times exponential of minus t by r. That is the expression of your exponential discharge. So now, what is this V of 0? It's given in the question that designer wants to discharge this from 3 volt to 1 volt. So this is V of 0, right? At t equal to 0, and then this is at uh, when the discharge process is completed, right? So this would be your V of 0. Your V of 0 would be 3, and your V of t would be 1 volt. And for exponential discharge, this t is 50 microseconds. So this will be 1. This is exponential of means t by RC. Now, from this, you can simplify it, and what will be R? Take this exponential, on the left hand side, and then take ln on both sides and tell me what is the value of the R in terms of T and C.
Yes, sir. We have to take both sides by log.
Yeah, first take this on the left hand side and then uh, take logarithm to the base E on both sides and then tell me what is the expression of R that you will get. Your R would be equal to T whole divided by your C ln of 3, right? So now, so your 200 whole divided by Vg minus 1, right? With this R is equal to this, right? And what is T? T in our case would be this 50 microseconds. So write 50 times 10 to the power minus 6 whole divided by uh, capacitor is 1 microfarad. So this is 10 to the power minus 6. Right? This C. And then you have ln of 2. Okay. So from this, what is the value of the VG that you will get? Because that is what you have been asked, right? So you need to find the value of the gate voltage that's supplied. What is the value of the VG that you obtain? You can simplify it further as following. You can write this as VG that is equals to 1 plus 4 ln of 3, right? If this and this
Yes.
goes, and then if we simplify it, this would be this. So now, what is VG? 4 times ln of 3 is 4.394. So VG is 5.394 volts. That is a VG. This page. Now, what about this problem? Now the discharge is no longer exponential but linear, right? Now, for linear discharge, your MOSFET has to behave like a current sink, right? Has to behave like current sink. So where do we need to bias the MOSFET? Bias the MOSFET in saturation region, okay? So bias the MOSFET saturation region, okay? So your I, that is CdVC by dt. What is this? VC. This is the voltage across the capacitor at some time t, right? This is current flowing through the capacitor, and this is the value of that capacitance. I is C dV by dt, right? And is this clear?
Yes, sir.
Okay. So then can write this in incremental form. C delta V C by delta T. Okay. The reason I'm able to do this is because this is a linear discharge, right? So the slope would anyway remain the same. So now, what is the current in saturation region? That is here mu n C of by 2 W by L. Then we have VGH minus VTH whole square. And that is equals to C delta VC by delta T. Then this implies on rearranging, we'll get this that your VG is equal to VTH plus square root of 2C delta VC whole divided by mu n C of W by L delta T. This is equal to 1 plus your square root of this is 2, C is 1 micro. Delta VC is difference between initial and final, right? 3 minus 1, that will be 2. So you'll write 2 all divided by mu n is 1000 centimeter square per volt second, right? It was given. Similarly, Cox is 0.5 micro, right? And your W by L is 10. Plug in these values. It's 0.5 micro farad per centimeter square times W by L is 10. And then we have 10 to the power minus 3 as delta T. Why? Because linear discharge happens in 1 millisecond, right? Then uh, put in the values and let me know what is answer that you are getting. What is VG? This is your VG, right? So what is the value of the VG that you obtain?
Okay, sir.
It's 1.8944 volts. Then you had problem number 3, right? And for this, MOSFET characteristics were shown. The values of the linear region threshold voltage VT and the MOSFET unscaled process parameter beta n, which is equal to mu and Cox. You need to, you were supposed to find the values of those two, right? Yeah, your VT and your beta n. And it's given that your VDS square is small in the linear region and it can be ignored, right? So if we assume that our VDS is very small, what would be the IDS equation? If VDS is very small, you can ignore the quadratic term. Then it would be KNW by L. This is your VGS minus VT times VDS, right? There's your ID1. I can write two equations, right? D1 and ID2. K and W by L would be same, right? Because these are my current values corresponding to the same MOSFET. Uh, and my VG and VD would be different, right? So would be VGS1 minus VT times VDS1. Similarly, this would be VGS2 minus VT VDS2, right? And if I take the ratio, what is ID1 by ID2? This would cancel out, right? I'll be left with VGS1 minus VT VDS1 divided by VDS2 minus VT VDS2. Okay. So then you'll pick the values of the currents for VGS and VDS from this plot. Okay. Let me do that. Your VGS1 is 5 volts, right? And your VDS1 is, suppose I give you this info, right? Similarly, your VGS2 is 4 volts, and your VDS2, that is same, right? 0.25 volts. So at this particular VDS voltage for two different gate source voltage, I'll give you the value of the current. Okay. For the first case, yeah, ID1, that would be 0.6 milliamps. For the second case, which is ID2, current is 0.4 milliamps. Okay. Now, can you determine what can you determine from this? If you are given this, what can you find from this equation? VT, right?
Sir, GG.
VT. Right? This is given, this is given, this is given. I mean, everything is given except VT. So the only unknown left would be VT. So if we solve for VT after plugging into the above equation, we'll get following. We get 0.2 VT, that is equal to 0.24 minus 0.20. And that is your VT is equal to 0.2 volts.
Yes, sir.
Fine. And what else we need to compute? We computed this, right? VT is done. And you also need to compute this B10, right? Mu Cox. So mu Cox, so your mu Cox is actually this, right? You call it B10 or Kn, whatever you want. Let's take this equation, right? From first, your ID1 is Kn W by L VGS1 minus VT times VDS, right? And what is your ID1? ID1 is 0.6 milliamp. So it's 0.6 milliamp. That is equal to the Kn. What is your W by L? Okay, we need to take it ourselves. Okay, let's take W by L of 100 by 2. Okay, we'll assume that. So VGS1 is 5 minus VT we have computed 0.2 times VDS1. VDS1 is 0.25. From this, we can find the value of gain, which is here, this mu CO. And the value that you get is 0.01. This would be, yeah, ampere per volt square. So we are done with this part. Was there any other problem that was left as assignment? Okay, this was left as an assignment, right? Problem number 9. Okay, I guess now let's go to today's topic. So let's start the week 9 session. We just had a brief
Problem
recap
number
of,
9.
yeah, number 9. Yeah, 9.
Problem number 9.
Problem number 9. Just
Uh,
a sec.
kindly repeat, sir.
Okay, just a sec. For problem number 9, I have already discussed in a video that have me posted as a comment. Then go to this week 8 video and uh, see the posted comment, and there this problem has been discussed. Okay, so let's save time that and start with problem. I mean, sorry, week 9. So let's skip the guidelines. So in last week, we covered the following topics, right? These topics were covered by the instructor. You were introduced to compound semiconductor, uh, basics of heterojunctions were uh, discussed briefly. The band diagram of heterojunctions was also uh, discussed, and you were also you also read about it, heterojunction transistors and three nitrides. Okay, so what I'm planning to do is I'll try to briefly recap this compound semiconductors instead of showing problems on this. I'll briefly address doubts if you have any, or revise some portion of that. So, do you have any specific query or problem regarding these lectures from the last week?
The band diagram of heterojunctions and heterojunctions transistor. Transistor.
Okay, okay. I will come to that as well. Just a second. First, sure. Yes. Okay, first let's start with compound semiconductors. I can briefly try to discuss them. So, what are compound semiconductors? Did you go through last week lectures?
Metal, sir, and uh, get wires
Now, your compound
and
semiconductors, uh, they are semiconductors that are made up of uh, two or more than two elements, right? For example, you
yes,
have,
yes, sir.
for example, gallium arsenide, right? This is a binary compound semiconductor. Why binary? Because it's made up of two elements, right? Similarly, you have gallium nitride, indium phosphide. It's usually one element from group 3, one element from group 5. Right? Here, there's phosphorus, arsenic, sorry, nitrogen, phosphorus, arsenic are elements of group 5, and gallium, aluminium, indium, and so on. These are elements from group 3. So any combination of them can result in a this what we call as a compound semiconductor. And among them, special class is binary compound semiconductor in which only two elements are present, right? What if we exceed that? Say, let me quote an example. What about this indium gallium arsenide? How many elements are there?
So
Three,
three type.
three, right? There are
Yes, sir.
three elements. So if I used a binary for these, what should I use as prefix for these compound semiconductors? They will be ternary, right? Because ternary means three, right? So this is ternary compound semiconductor, example of an ternary compound semiconductor. So whenever you have this ternary compound semiconductor, there is, uh, I mean, we don't write, but this is what we assume, right? This is X mole fraction and this is 1 minus X, right? X of indium and 1 minus X of gallium. So your uh, material properties can vary based upon the value of this X, right? For example, if your X is 0, then this would be what? If X is 0, then what is this compound?
One.
This would be gallium arsenide, right? Because if this is 0, this is 1 minus 0, which is 1. So this is gallium arsenide. So when your X equal to 0 corresponds to gallium arsenide, right?
Yes,
And what if we
yes, sir.
vary X all the way till 1? If you vary X and put the value of X as 1, then this would be indium arsenide. Why? Because this would be then 1 and 1 minus 1 is 0. So there won't be gallium. It should be indium arsenide. So, I mean, this is a rough estimate to show you that in such compound semiconductors, I mean, the material can change based on the values of X. And it's not, I mean, we cannot only, not only can we take the values of X as these whole numbers 0, 1, but we can also take the fractions. I mean, X can be fraction as well, right? It can be 0 0.2, 0 0.1, 0 0.3, 0 0.4, all the way till 1. Okay. So your lattice constant will be a function of this X, right? And similarly, your effective mass will also be a function of X. So your lattice constant will be a function of x, your effective mass will be a function of x, and your band gap, that will also be a function of x, right?
So everything depends on X, sir.
Yeah, it depends upon x because x, I mean, altogether change the nature of this material, right? I mean, we just saw if x is 0, then this is gallium arsenide. And when x is 1, this is indium arsenide. And these two are completely different, having completely different properties, and lattice constant is different, effective mass is different, EG is different. So, what if you are interested in, uh, say, finding particular value of uh, lattice constant corresponding to some value of x that falls between 0 and 1? Is there any law that helps us doing that? What is that law that helps us in doing this? I mean, this particular law was discussed, right? The Weber's law, right? Suppose you have uh, following. Suppose you have this aluminium, gallium arsenide, right? As I said, this would be X and this would be 116, right? And when the value of the X is 0, what would this correspond to? What is the material here at X equal to 0?
GaAs.
It will be what? Yeah, that is what GaAs, that is gallium arsenide, right? So
Yes, sir.
this is your gallium arsenide. And what is a material when X is 1?
ALAS.
Yeah, that is aluminium arsenide, right? So experimentally, we do have info. Uh, Say I tell you that your gallium arsenide, lattice constant of the gallium arsenide is 5 angstrom. Suppose this is an angstrom scale. This is 5. This is say 4. Right. Suppose these 2 points you know. Is this clear?
Yes, sir.
So it's 5 angstrom for gallium arsenide and 4 angstrom for aluminium arsenide. So what if I tell you, tell me what would be uh, the lattice constant for x equal to 0.6? I mean, intuitively you will say that it will fall somewhere between 5 and 4. But say I tell you tell me the exact value. What would the value of the lattice constant be? So there is an empirical law that helps us in determining that. That is your Weygard's law. Okay. So what Weygard's law states is following. Suppose the property of interest is lattice constant. I'll write lattice constant of this aluminium, gallium, arsenide. Right. This would be equal to your x times lattice constant of aluminium arsenide, right? Plus 1 minus x times your lattice constant of gallium arsenide. Okay.
Yes, sir.
Let's see if we get these two values. We know the lattice. Let me write that so that we don't get confused. The lattice constant of aluminium arsenide. What is that? That is 4 angstrom, right? This is 4 angstrom. And we also know that the lattice constant of what? Aluminium arsenide is done. Then we have gallium arsenide. For gallium arsenide, it's what? This is
0.6, sir.
0 point. Wait. It's 5
Uh,
angstrom, right?
6.
For gallium arsenide, it's 5 angstrom. So now, say, uh, for also I know that for x equal to 0, this is gallium arsenide, right? So if I put x equal to 0 in this, if I put x equal to 0 in this, would be what? For x equal to 0,
Would be, sir,
this reduces to lattice
four-
constant of
four angstrom.
aluminum arsenide, right? And that is what?
Yes.
X times this. So this term would not be there, right? Why? Because x equal to 0, this would cancel out. I'll be left with
Oh,
1 minus 6. 1 minus 6 would be 1 because x is 0. So this would be 1 times lattice constant of what? Gallium
gallium
arsenide, right? Sorry, I wrote this by mistake, right? Which is actually the case. I mean, since we know this is 5 angstrom, if you put it here, the lattice constant of gallium arsenide is indeed the lattice constant of gallium arsenide from this formula, right? Similarly, you can confirm if you'll put x equal to 1, you'll get lattice constant of aluminium arsenide is equal to this 4 angstrom, right? From this table, if you use x equal to 1 in this equation. Now, I had earlier posed a question, what about this x equal to 0.6, right? Now, if x is 0.6, that would be, let's write that compound. It would be aluminium 0.6, gallium what? 1 minus 0.6 is what?
0.4.
0.4, right? That would be, what is x? 0.6 times. That is constant of aluminium arsenide. That is 4, right? Plus what? 1 minus 6. 1 minus 6 is 0.4
0.4 into 5.
times 5, right? So what is this? 4.4 angstrom. Okay, so
4.
you'll say that this would be 4.4 somewhere here. Is this clear?
Yes, sir.
So this is your Weygard's law. I mean, you can similarly use it for effective mass. And for band gap, uh, it's not necessarily a linear relation. Uh, there is a little bowing uh, in band gap versus
Exponential,
X. Sorry.
exponential relation.
No, I mean not necessarily exponential. The thing is that it won't be linear. So there would be some quadratic component as well. I'll discuss briefly that. So if you're this, what we say, suppose this is EG, right? And suppose I take the example of aluminium gallium nitride. This would be X, this would be 1 minus X, right? So this is what for X, right? This is X equal to 0. When X is 0, this is gallium nitride. And the band gap of gallium nitride is 3.4 eV, right? And when X is equal to 1, what is this? When X is 1,
Zero,
aluminum nitride,
zero,
aluminum nitride, right? And what is the band gap of aluminum nitride? Sorry, I was not able to hear it.
uh, 4, sir.
Can you quickly search on web what is the band gap of aluminum nitride? Search it on Google and let me know. Band gap of aluminum nitride is greater than this. But what is the exact value? So let me write that I gave enough time. This is 6.1 eV. Okay. The band gap of aluminum nitride, which corresponds to X equal to 1, would be 6.1 eV. So
Yes, sir.
this is your trend as per what? As per this law. But turns out that there is some bowing, right? So this is a non-linear increase. This is not a linear increase, right? The slope here is not the same as slope here, right? So let me write the equation that is followed in case of band gap. So the reason I took the example of aluminum gallium nitride is because this non-linearity in band gap is uh, way more evident in this compound compared to others. In others, the non-linear trend is also there, but in this particular compound, this non-linearity is more prominent. So the band gap of aluminium gallium nitride, right? This band gap is equal to X times Eg aluminium nitride plus 1 minus X Eg gallium nitride, right? This is Wegener's law, right? But since there is some bowing, right, as a result of a nonlinearity, so we have this quadratic term. So let this be B x times 1 minus x. I notice x and x is x squared, so this would result in minus x squared. This b is a constant, which would be your Boeing parameter. Right? This is your Boeing parameter. Right? And how is this Boeing parameter determined? We determine it experimentally, right? We experimentally make this main compound corresponding to some x equal to 0.1, x equal to 0.3, 0.5, 0.7, and then determine the values of the band gaps, and then we fit a curve, and then determine this Boeing parameter that will fit those experimental data. Okay, that's how we compute the Boeing parameter, and that's how the trend in band gap differs from uh, the rest of the material properties. So that finishes your what? Uh, that finishes. Okay, we discussed Baker's law. We discussed the case of band gap as well. And then you have what? Just a second. Then heterostructures were discussed, right? And the interesting thing about them is that, I mean, what are heterostructures first? An example that I can take is suppose you have this compound semiconductor, right? Gallium arsenide, gallium arsenide, right? Suppose your indium gallium arsenide is sandwiched between these two gallium arsenide layers. Right? This would constitute an example of an heterostructure. So the band gap of your gallium arsenide is around 1.4 eV, and the band gap of indium gallium arsenide, that is 1 eV. So this would constitute a quantum well, right? This would be, if I draw EC, this is your EV. This is 1 EV, and this is indium gallium arsenide. This is 1.4 EV. This is your gallium arsenide. Right, so an electron would be trapped here, and likewise a hole will get trapped here. Right? And treat this as a particle in a box. So what else was discussed? And then there were types of heterojunctions. Um, Heterojunction is formed when you, I mean, have different materials, right? For example, suppose this is material A, this is material B. You join them, and then you'll have heterojunction, and right? And based on the relative band gap values of the two, you'll have uh, type 1, type 2, and type 3 heterojunctions, right? Your type 1 is your where uh, you have this straddling band alignment. Then you have staggered type in which the uh, band gap alignment is staggered. This corresponds to type 2. And then you have broken. Right, let me quickly draw how straddling band alignment. In straddling band alignment, which corresponds to case 1, this is your wide band gap material. And this is your narrow band gap material. So this is straddling structure, right? This is the heterojunction. This is your type 1, which is straddling band alignment. And then you have type 2. In type 2, you have staggered alignment, right? Staggered alignment looks something like this, right? And then you have broken gap, which is type 3, right? This is your PG1, this is your PG2. And these heterojunctions they are formed based on the band alignment and their electron affinity values, right? Uh, this was discussed. So let me do one thing. Um, I'll discuss the band diagram of these heterojunctions and some problems if I get time in the next session. Meanwhile, if you have any doubt regarding what we, uh, I mean, recapitulated today, including the assignment problems
Sir,
from weekend.
three type of uh,
Sorry,
three type of band gap of heterojunction we have got
this one.
type 1, type 3, 2, and type 3.
Yeah, this is your
The
type 3.
uh, type 3 and type 2, how we can get?
Okay, you are saying
Type
probably
2,
how will you
type,
result in? Hmm?
uh, yes, sir.
No, yeah, I got the question. Just a second. Okay. Probably share a diagram and make it more illustrative. So see, in type 1, notice your conduction band and valence band. They are positioned entirely. Wait, this is your straddling. Yeah, in this, your conduction band and valence band of one semiconductor is positioned entirely below the conduction and valence band of the other semiconductor, right? If that is the case, that would be your type 1 straddling. But your question is the difference between this staggered and broken type. this is your
Yes.
staggered, and this is broken gap, right? In staggered, the conduction band of one material is positioned below the conduction band of the other, while the valence band is positioned above the valence band of the second. Right? Notice here valence band is below the valence band of the other. Right? Here
Yes, sir.
conduction band of this comes below this, and likewise here valence band. I mean, in terms of holes, I mean the energy order. If we talk in that sense, then we can say that the valence band of the first material is positioned above the valence band of the second.
Yes,
But
sir.
uh, and examples of this would include uh, these are the two examples. Right? This is tungsten here. Lovely. So, and in broken gap, the conduction and valence band of one material, they are positioned between the uh, conduction band and valence band of the other.
Yes, sir.
Uh,
Type on, sir, balance, uh, uh, balance,
See, I think I have drawn it a little
balance band.
wrong. The thing is, this the conduction band of this comes even below this. Then a broken gap will be formed, right? Here, this conduction band is anyway above this, right?
Yes, sir.
So if this comes below this, I mean, or in other words, it comes below this gap, forming gap of the other, then it constitutes a broken gap, and that is your type 3. And the examples for this would include, I don't have any example for this. Uh, do search
On,
it up if you,
type on,
yeah.
sir. Type on is greater than balance band, sir.
Notice here valence band. Okay, see how type 1 is different from type 2 is that in both conduction band is below the conduction band of this, right? This conduction band is below this
Balance,
conduction band. Agreed?
yes, yes, sir.
But the valence band, the relative arrangement of valence band is different. Here the valence band is below this level, and here the
Yeah,
valence band is above this level. So this you call straddling, this you call staggered. And broken gap is altogether a different type, right? Where even this conduction band comes below this, right? It comes even below this. There is some, I would say,
conduction band
difference here as well. Yeah. This
is
is
same.
valence band and this is conduction band of the other.
Conduction band same, sir. In type 3.
In type 3, no, conduction band is not same. It comes even below this valence band of material first. This is material first, this is material
Yeah.
second. And
Yes, sir.
this is EC, this is EV. This is EC, this is EV. Let me
Oh,
make this 2, 2, 1, 1. So notice
yes,
yeah,
right.
EV1 is above EC2.
Yes, sir. Yes, sir.
That is, I mean,
Understand.
I'll still look into it in more detail, but this is what I know about these types of heterojunctions. So any other doubt?
No, sir.
Okay, thank you. Then we'll end the session today. Okay. In the next session, we'll discuss the band diagram of heterojunctions, followed by a few problems on heterojunctions, and see if we get time for the other problems as well. Okay, thank you.
Yes, sir. Thank you, sir.
Thank you.